Welcome back. In our last video, we did the single most important job in machine learning. We took raw, messy data and made it clean, structured, and ready to use. We learned the garbage in, garbage out principle. Now we get to do the really exciting part. We'll use that clean data to build our very first model and make predictions. Today, you'll learn the two fundamental types of supervised models and, most importantly, how a computer actually learns. As we learned in B1, supervised learning boils down to two main jobs. The first is regression. This is when we want to predict a number like the price of a house or the temperature tomorrow. The second is classification. This is when we want to predict a category like spam or not spam, cat or dog. We're going to start with regression because it's the most intuitive way to understand how models learn. Let's build a linear regression model. The linear part just means line. The goal is to find the single best line that describes the relationship in our data. Imagine we have our housing data. On the x-axis, house size, and on the y-axis, price. Linear regression finds the perfect line that cuts through the middle of those data points. This line is our model. Why? Because now, if we have a new house size, we just trace up to the line, look across, and that's our price prediction. The whole model is just the simple equation for that line. Y equals mx plus b. But best fit is a vague term. How does the computer quantify best? It does it by measuring error. For any line we draw, we can measure the vertical distance from every single data point to that line. This distance is called the residual or just error. A good line will have very small distances. A bad line will have huge distances. The best line, therefore, is the one that has the smallest possible total error when you add up the error from all the points. This leads us to the most important concept in all of machine learning, the cost function. A cost function is just a formula that boils down all those individual errors into a single number, a penalty score. Think of it like a golf score. The lower, the better. A common one is mean squared error, or MSE. It sounds fancy, but all it does is 1. Take every single error, 2. Square it, which makes them all positive, and 3. Calculate the average. The result is one number. A high number means a bad line. A low number means a good line. The model's entire goal is to find the line that gives the lowest cost. So, what does this cost look like? If we could magically try every possible line, every combination of slope and intercept, and plot the cost for each one, we would get a shape like this. A smooth valley. The high points on the rim of the valley are lines that are a terrible fit. And the single lowest point at the very bottom of the valley represents the one line that has the lowest possible error. This is our best fit model. The entire game of training a model is just finding the bottom of this valley. So, how do we find the bottom? We use a process called gradient descent. This is the classic analogy, and it's perfect. Imagine you're standing on that foggy error mountain. You can't see the bottom. What do? You feel the slope under your feet. That slope is the gradient. You take one step in whatever direction is steepest downhill, then you stop, feel the slope again, and take another step in the new steepest downhill direction. You just repeat this. Step, check, step, check. Each step is an iteration of the model learning. Eventually, you'll end up at the bottom. That's exactly what gradient descent does. It steps its way to the line with the lowest cost. Great! We now understand how regression works. Now let's look at the second task, classification. This is where we predict a category, not a number. The simplest version is binary classification, 2 groups. Spam or not spam. Here, our goal is different. We're not trying to find a line that fits the data. We're trying to find a decision boundary, a line that separates the 2 groups. The learning process is very similar. It still uses a cost function and gradient descent, but its goal is to find the line that makes the fewest mistakes in separating the classes. So, how do we know if our classification model is any good? The most obvious metric is accuracy. What percentage of predictions did the model get right? If we tested on 100 emails and it correctly identifies 95 of them, that's 95% accuracy. Simple, right? But accuracy has a huge hidden trap. Imagine a dataset where 99% of emails are not spam and only 1% are spam. A model that is lazy and just predicts not spam every single time will be 99% accurate. But it's a completely useless model. This is called the imbalanced data problem. Because accuracy can lie, we need smarter metrics. The first is precision. Precision asks a very specific question. Of all the times the model predicted spam, how many times was it actually spam? This is a measure of quality. If our model says 10 emails are spam, but one of them is actually an important job offer, our precision is only 90%. We want to avoid these false positives. High precision means that when the model does predict something, it's very likely to be correct. The other side of the coin is recall. Recall asks a different question. Of all the spam emails that actually existed, how many did our filter catch? This is a measure of completeness. If there were 10 spam emails and our model only caught 8 of them, our recall is 80%. We missed 2. These are called false negatives. In the real world, there's almost always a trade-off. If you make your spam filter really aggressive, high recall, you'll catch all the spam. But you'll probably send some good emails to spam, low precision. It's a balancing act. Let's recap. Today, we learned an incredible amount. We learned about linear regression for predicting numbers. We learned the intuition behind how models learn using a cost function to measure error and gradient descent to minimize it. Then we learned about classification for predicting categories and why accuracy isn't enough, leading us to precision and recall. In our next video, we're going to put this to use and build 2 of the most popular and powerful classification models, logistic regression and decision trees. You won't want to miss it. Subscribe and thanks for watching.